and would like to move now to the second presentation for today. That is going to be given by Joe Waxse. Talk about the phase levee investigations in Louisiana. Joe, the floor is yours. You still have yourself on mute. You have to unmute yourself. If you go to the control panel and just click on the microphone.
There we go.
There we go. Very good.
Yeah, I was trying to unmute, but it didn't work. Well, thank you very much, Daryl. It is a great honor and pleasure to be here today to share with you. And I'm Joe Waxse. I'm a senior consultant, semi-retired. I don't think I'll ever retire until I'm no longer able to make informed decisions. But we're going to talk today about a phased levee investigation program that we did after Katrina. In 2005, I was actually in the process of moving to San Antonio to join an office that Terracon purchased in San Antonio when I got a call from my friends at the Omaha district saying, hey, we'd like Terracon to team with us to go down to Katrina, go down to New Orleans and help out the New Orleans district, and we want to do a demonstration program. So we agreed to make sure this works. So this was the stretch of levee down south of New Orleans that we were doing the demonstration program on. And we had Terracon's responsibility was laboratory testing and in situ testing and geophysical. The main focus of our program was to show the effectiveness of CPT and geophysical screening before you do your borings, and then comparing the borings to the in situ testing and the geophysical. This hadn't been done much down there, and we felt that after, with the scope of work that needed to be done for the levee repairs post Katrina, we felt this was very important. So basically, we had Paul Main as our in situ testing consultant, and we had Rick Olson with ERDIC, the Cone CPT guy, and laboratory testing specialists within Terracon to help set up this whole program. The first thing we demonstrated was the geophysical, and we tried various methods. We tried ground penetrating radar with as low a frequency of transmitter as we could physically use, which would go deepest. It had a GPS unit on it to track its location and was towed along the line with the ATV. The operator could see the screen results as he was going. We did one down the center line and one down both toes. Unfortunately, the GPR didn't penetrate the high plasticity fat clays very well at all. Did not get a whole lot of useful information from the GPR, so I'm not going to spend any more time on that. We did electromagnetic, same sort of profiles. That gave us a little bit more information, but it didn't seem to have a great correlation with the stratigraphy that we were seeing in the CPTs. This is with the EM61 and this is EM31. And you do kind of see the upper levee materials over the fat clay, but it wasn't great detail. So the next method we tried, yeah, that's basically not much results from the EM. But then we used the AGI Advanced Geosciences Inc. Super Sting, which is a 112 probe multiple electrode resistivity device. And what it does, you put in these stainless steel probe rods at 10-foot centers for 112 probes, 1,100 feet. And you basically measured the winter array between all sets. So you've got small areas that move up and down the line. You've got deeper areas. Each one of these spots is representative of a measurement. And when you use all that data in AGI's proprietary modeling program, this is the kind of results you get. And this shows some CPTs. There's a sand layer. You see there was better correlation, not perfect correlation, but better correlation and a lot deeper results. This is the full depth. You can see the thickness of the Pleistocene clays and getting into the stronger materials below, down at 250 feet. We also tried this in a marine setting because along each one of these levees was a barrel channel, and you can tow a floating string. We tested that out. What we found is that we didn't get as good of results, and we had lots of trouble with duckweed getting accumulated on the lines and causing problems. So we didn't use that in the rest of the program, but we just did a test line. This is an example of the MER results on a stretch of levee, where using multiple electrode resistivity analysis is kind of like looking at the soils through Coke bottle glasses. You get fuzzy results. It's not good for giving you exact delineation of stratigraphy or strength or anything else, but it shows you where you have changes. And this was an area that we said, whoa, that looks so different. We need to do more work here. So we took the cones that we had, and Rick Olson did a heat map of shear strength based on all the cone data. And what we saw is a deep channel full of clay, soft soil, very weak material. You can see the scale down here. Red is soft, very soft. Blue is stiff. So you've got soft layers, and then here in this area, you've got a very deep. So this turned out to be a prior flood channel that was unknown and wouldn't have been caught without because we were doing CPTs. Okay, the standard methodology that the Corps was using is that they would do borings every 2,000 feet. And these borings were 5-inch samples, 4 foot long, taken continuously, and test the heck out of it. And it was just basically put every 2,000 feet. So without the multiple electrode resistivity, you very likely would have missed this with the boring. What we were able to show is that the CPTs could be done much more economically, and we could do approximately 5 to 8 CPTs for every boring cost. And so we went on 200-foot centers instead of 2,000-foot centers through areas of interest like this. And this is the kind of detail that we were able to get. If the boring did happen to hit that, they may have designed the entire 2,000-foot stretch represented by that boring for this condition, when it's only actually 300 feet long. This is another MER result that we got and said, ooh, we got to go see what that is. So we did multiple lines and did a 3D imaging of that area. And it turned out, this is a cool modeling that you can turn on and turn off various levels of electric conductance. And what we saw is a deposit of something there. So when we went back and we drilled in that area, we found wood. There, it basically was another prior flood channel that was filled with wood. And that was a kind of a deep layer of wooden roots, but that wouldn't also have been picked up without the MER. The cone penetration test with pore pressure measurement, we put on a marsh buggy. And the reason we decided to do this is because this is a locally available rental option with the repair shop right there, the operators right locally. We used local personnel to drive it. And we put a CPT unit, and this thing is very heavy, so it had plenty of reaction to push the CPT. And this is a hollow core jack with jaw clamps that basically extends up 3 feet. You put a rod on it, push it down, put another rod on it. This is the de-airing vessel for de-airing the cones. When we first started, we used de-aired water-filled cone units. You can see once the tip is put together with the porous stone in there that's been de-aired, we put a condom over it to keep it from de-airing until we got it in the ground. And here's the cone results. You see very soft soils down to a sand layer at about 7 feet, clay, interlayered sands and clays, and then deep normally consolidated clay below 15. So that's a typical cone. You didn't want to swim in the bayous out there. There was all kinds of alligators and snakes and snapping turtles. So this is why we use the marsh buggy, is that it could go down a channel, climb up a 2-to-1 slope, and go out across the bogs, through brush. It was a very aggressive unit that could get anywhere with minimal damage. We did in situ vane shear. If you are familiar with cone soundings, you can get shear strength from the cone data using correlations with other types of shear tests. And the gold standard of what's your shear strength is the vane shear. And this is a device that the vane is up in that housing. You push it with the cone, and when you get down to test depth, you basically knock it free from the housing, push it in with this inverted little device. I invented that, but it basically pushed the vane out of the device. Then you set the unit. This is a Geotech electronic vane, and this turns at a very slow rate in accordance with ASTM. And it gives you, and then after the test, you pull it back up. You have to rotate until you find the slot, and then you pull the vane back up in the unit, and you can go down to the next test step. And this is the results. This is degrees of torque, but this isn't the vane moving. This is the rod torquing and torsion. And you take it up until you get a flat line. That's your ultimate shear strength. And then you can turn the rod. They say 25. We did testing and showed that 5 revolutions was enough to get to remolded, but we did 10. And this is the remolded strength, and that's the ultimate strength. So now you know your sensitivity. And we do those at various depths, and we do the cones first and then decide we need to characterize that strata, and we'd go to that location and depth and get the vane shear. So the Omaha district was in charge of sampling, and they had their rigs out there pushing these 4-inch diameter, or is it 5-inch? I can't remember. Diameter 4-foot long tubes. They were quite heavy. This is the Horslov sampler. They got very good quality samples, but we needed to make sure they weren't disturbed, so we had foam bottomed containers, and this is how we would run the samples to the laboratory. And for this job, this was our area where we were doing the levee investigation, and we set up a laboratory right here. The laboratory was a bunch of remote office buildings. This is an extruder I had built for the 4-inch diameter tubes. And this, I went to Home Depot and got cabinets, and we got geotack. These are all consolidometers, and they were large diameter consolidometers for the full 5-inch sample. I think they were 4-inch diameter consolidometer cells. That was in one trailer. That's the extruder. That was run by a portable hydraulic motor. And we'd extrude the tubes out onto the trays that we built to carry the samples. They'd be wrapped and staged for classification. We'd put them up on the table, do very detailed. We'd cut a thin revealing strip along the top and do a very detailed classification. And we had to learn the New Orleans soil classification system, which is different than any other classification system in the world. It has 4 or 5 different organic soil descriptors that you have. It took some training and it took some practice to get their method down. And then we cut the samples and assign tests, and we had core personnel there to agree on what testing to do. These were consolidometer tests. This is unconfined tests, UU tests. And these samples would be extruded and tested within 48 hours of taking them out of the ground. And that's a significant difference from their practice down there. Typically, they'd take these samples, put them in wax, and they'd sit for up to a month, 2 months before they were tested. With this program, we did the testing immediately after the samples were obtained. And their standard procedure is to do sets of 3 UU tests on 1-inch by 4-inch samples that have to be trimmed out of your specimen. So this is a UU test sample. We used the fall cone device, which is basically a weighted cone, different cone weights, that's dropped a specified height into the top of a sample, and you determine the shear strength by penetration. And when we started getting these and comparing them to the UU, the cone data, the in situ vein shear, we had basically double what we were getting with the rest. And we talked to the fall cone manufacturer and said, we think you have TSF instead of KSF. And they said, oh no, that's impossible. We couldn't get agreement from them, so we stopped using the fall cone. The direct simple shear device, that's a very sophisticated shear strength test. It's the gold standard of laboratory shear strength tests. 2 rings of soil carefully trimmed into these rings, and you trim them. There's 2 rings here that are forced over, and they're covered with steel, washers basically, and the washers will slide relative to each other. You have to pre-saturate it. So you're putting it in a membrane, putting the sliding rings around it. And the geotech machine applies a vertical pressure and a horizontal shear stress, and you run it very slowly after you have saturation. And you get very good CFE data. So we didn't run a whole lot of those, but we ran enough to feel comfortable with our results from the in situ vein shear. Consolidation tests, pretty standard, except they were large diameter. We use the miniature vein in the laboratory. This is an offshore device that I used when I worked for McClellan Engineers offshore. You can take a tube, put the vein down in the Shelby tube. You turn this spring to create a torque, and on the top, it's got an indicator that shows you how far your vein went before it sheared. So you then look at the degrees on the torque plot of strength versus torque, and you get a shear strength. The triaxial, UU triaxial tests were run saturated. with the 1 inch by 4 inch samples, put them in the membrane. We wanted to use air. They said, no, we can't use air. You need to use water. So we used water. And this is a failed sample after the test. And here's the typical UU, 3 specimens at 3 different confining pressures. As you would expect, get very little difference. It's a UU test. We also did unconfined on full samples, the 4 inch samples, so that we had no trimming, and it tested a larger diameter sample with the conventional unconfined compression. So basically, we did this all within 6 weeks of award of contract and got a whole lot of data for this area, and that's a failed unconfined. And we would map the failure surface and get degrees and draw pictures of it on the test sheets. This is the unconfined results. So now we get into the data correlation, and Paul Main, the core, myself, other Terracon lab people agreed that on the correlation presentation to give to the core to show the results of this. This is the shear strength determined from QT net, which is a cone shear strength correlation. That Paul Main is a big believer in using pore pressure for shear strength evaluation. This is according to U2 correlations. This is the skin friction. So it's remolded shear strength that measured in the cone. So that should correlate fairly well with remolded strength. These are the 3 UU tests. You can see the UU at the high pressure had better correlation than the 2 lower pressure tests. But a lot of the UU data was well below what you would interpret from the cone. The unconfined tests showed very good correlation. So that was a revelation, is that the simple unconfined test actually gave us better correlation with the data than unconsolidated undrained triaxial. This is the fall cone. I told you it was twice what we thought it was, but we couldn't get buy-in by the fall cone people to change their plot, so we didn't use it. This is the mini vein. Shows very good correlation with the cone data. This is a simple shear test, and the simple shear red is that at existing overburden pressure, which you would expect to correlate. And you have pretty good correlation with the direct simple shear. This is the vein shear. This is that gold standard with the appropriate correction for plasticity. And we ran Atterbergs, a lot of Atterbergs on these. So I would say that the cone and the vein showed, hey, you've got strengths up here, whereas the UU tests, which they typically had been using, are way lower, which will give you. And the other thing was the consolidation tests would give a pre-consolidation pressure, some of them that was below in situ overburden pressure, and we just don't believe that. You always have disturbance when you're sampling, extruding, trimming, putting it in the device, and always be skeptical of laboratory consolidation tests as far as pre-consolidation pressure. So we were able to demonstrate on that project that if you use multiple electrode resistivity first, you find the areas that you need to define what's different there, because there's something different. You find buried wood, you find old channels, you can determine, well, where can we spread out the borings on a wider distance and still get adequate data. So it was successful, except that when we presented it, we told them they were doing it the wrong way and they should change, and they kind of took exception to that. So we had a little bit of a struggle there for a while until we had repaired the relationship, and they ended up using this general program for the entire. I guess you'd say we lost the battle but won the war, in that we basically were able to contribute to better characterization of the soils down there. In 2011, we took the same thing up to the Missouri River Valley south of Omaha, where they had that terrible flooding that lasted forever, all summer. And these were areas that we did the same program on in Nebraska. Here are long stretches of multiple electrode resistivity showing areas of interest where we needed to focus. They did a lot of flood observation during that period, and they would tell us where the sand boils were, and we would indicate on there, these are areas where they observe sand boils. So you can see this shallow sand here compared to, there was pretty good correlation between the multiple electrode resistivity and the observed failures. This is just a typical stretch of levee saying, yeah, you certainly want a cone here. So we'd sit down with the Corps guys and we'd agree on, okay, let's do cones here, 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 you know, basically decide the CPT locations together. Then we go out and we'd run the CPTs. You can see the levee material, the underlying natural silts and clays, the sands. Gave us very detailed information on what, for their modeling and analysis of what they needed to do on the reconstruction. This is a boring overlaid with the same color mapping as the MER, and you can see there's not perfect correlation, never will be. The multiple electrode resistivity is not a precise mapping tool, but it does show you where things just generally are different and where you should look. The Corps guys actually took this a step further and figured out a 3D modeling effect to better accentuate the difference between the levee, the underlying clays, and the sands. So basically, this saved a lot of money in allowing the designers of the levee repairs to have better geotechnical information, consolidation, bearing capacity, et cetera, compared to the old methods, because we showed higher strengths. We reduced the risks of encountering unknowns by doing much closer spaced. And the Corps district pretty much uses this phased levee investigation in most cases today. So that's the end of the presentation, and I'd be happy to take any questions.
Joe, thank you very much. And as a dedicated conehead, many of you on the call know that I'm very much a proponent of CPT. I could not wish for a better presentation than this. It really shows the value of CPT.